Now we're going to look at our first example, and before we begin to look at the answer in detail, let's just make sure we all see the same perspective in this question, because it's a little tricky to see the intent, but the intent is that we have this rectangular plane here, right? And the intent is that it is sitting in the positive x, and here I'm going to put my positive z axis here, so that it's sitting in the xz plane perfectly. So that's the intent for the area vector. My positive y is up here. And we're given two electric fields to consider. The first electric field we're given to consider E1, and we're told that they both both E1 and E2 sit in the xy plane. So the vector E1 is at 10 degrees here, as shown from the positive y-axis. The vector E2 is down here, and at negative 25 degrees from the negative x-axis. So that's the perspective we're looking at. Now, before we do our calculations for flux utilizing dot product, the most important thing in starting your analysis is to correctly get your n-hat vectors in here, because that's going to be the vector we use in our dot product. And that n-hat vector, by convention, will point in the positive of the Cartesian coordinate system, so it points in the positive y for this plane, not the negative y, perpendicular to the plane. So now we're ready to go and utilize dot product to calculate our flux answers. So please pause the video at this point, see if you can calculate the correct flux values for E1 and E2 in part A, and then you will simply add and subtract those values to get the net flux, and we'll talk about those answers. So pause the video here. Okay, hopefully you've attempted your answers, and we can now compare and see about the solutions. Well, the first flux, flux 1, is given by E1 dot n hat A, so magnitude of the first, magnitude of the second, cosine of the angle between the two as drawn from a common origin. So our common origin is actually the origin in this case. Our 10 degrees, cosine of 10 degrees, gives us a positive answer. So we get positive 246.2 Newton meters squared per coulomb. And notice we do not put a vector answer with our solution, because dot product, right, is always a scalar. So no vector answer. How about flux 2? Well, flux 2 gives us magnitude of the first, 100, magnitude of the second, the area, which is 5 in this case, and cosine of the angle between the two is drawn from a common origin, the 115, and we get negative 211.3 Newton meters squared per coulomb. And those are our individual flux answers. So again, no x hat, y hat, z hat with our answers ever. It's a scalar answer. But just like with energy, we had energy in, energy out, we can have flux in, flux out, and that's how we talk about the net flux. So in terms of our net flux answer, we of course get the just addition and subtraction of the two fluxes. Our net flux is positive, so that's telling us that the net flux was in this upward or outward sense, and even though we use the language that's implying direction, we do not put x hat, y hat, z hats with our answer, and we'll see as we go along it is much more closely related. Flux is much more closely related to energy in, energy out than it is to even use the language of direction. But in this case, we would talk about it as a greater flux going upward than we would have a flux downward. So there's our solution. We're going to talk about a different area geometry, a cylinder, on our next example, but hopefully this one made sense.